Welcome everybody back to our course on memory device technology for AI/ML computing. So this is the final lecture. This is great conclusion after 60 lectures that we went through. And for the final wrap up, what we would like to do today is to give you a very brief overview of all the concepts that we studied in the course in the past 60 lectures. Also provide a future roadmap for this very exciting area of memory device technology geared towards artificial intelligence and machine learning based computing. And finally, I would like to also take this opportunity to acknowledge all the people who helped in running this particular course. Okay, so right at the beginning of our journey, we started looking at the key paradigm shifts, which also introduced us to the main motivation and the pain points of introducing this exciting area. Why do we really need to learn about memory device technology in and different computing paradigms? So as you remember, it all begins with a major shift in how we do computing in the first place. And as you can see on the slide, image that you're familiar with, which we have repeated several times, that we have seen a remarkable shift from logic-centric computing paradigm, which involves a lot of number crunching, to more data-centric computing paradigm, where the idea is to make sense of large amounts of unstructured data. And that, in a sense, is your AI/ML workload. However, this significant shift, as we moved further in our course, exposed a massive architectural flaw, especially from the perspective of computing systems. And that is what you can see over here. Over the decades, what has happened, as we discussed, the processor performance has scaled quite rapidly, but memory throughput, whether it is DRAM or it is the NAND flash, which is the main memory and the main storage, has lagged behind significantly. And this is what has created the significant difference in throughputs, which we termed as the memory wall or even the I/O bottleneck. So what happens when both these things are combined in the same landscape? Shift in computing paradigms towards data-centric computing along with this memory wall. What happens essentially, as we saw, is when we start running data-hungry algorithms like neural networks, this becomes the key bottleneck. It results in a severe energy penalty. And this energy penalty, as you can see from your familiar bar chart, it shows that while ALU access costs 1 unit of energy, but fetching data back and forth from the DRAM or from the main storage, from the flash, can cost up to 200 to 500 times of doing that ALU instruction. So basically, the problem or the bottleneck of modern day computing is that we are no longer compute bound. Memory accesses have become much more expensive than computing itself. And to address these key pain points, our course followed a particular arc. And in this particular arc, we started with classical von Neumann computing. Again, an image that you're very familiar with. And we saw that in von Neumann computing, you had completely segregated CPU and storage, and this was connected between the data bus. What we did essentially is we saw that several courses focus on this CPU or logic elements, but in this course, we wanted to focus specifically on the memory block itself. And we began by looking at the entire pyramidal hierarchy of memory and storage, from very fast SRAMs on the top down to DRAMs, storage class memories, and finally primary storage like NAND flash. However, we realized that in the data-driven compute paradigm, moving data back and forth, as we just discussed in the previous slide, creates this von Neumann bottleneck. And this realization forced us to look beyond von Neumann computing towards co-located logic and memory. And we traced this architectural evolution from single CPUs with severe memory bottlenecks to finer and finer grained parallel GPUs, and ultimately, as we saw, to new age neuromorphic computing. And this also motivated us to think that there is a radical rethink that is required across devices, circuits, and systems. And computing is going to fundamentally shift from logic to memory driven computing, where the memory elements are no longer passive storage elements, but they are essentially a computing resource. That is what we saw at the end of our course. But back to the traditional memory technologies that form the foundation of our current computing paradigms, which we spent several weeks studying. So just a very brief recap. Right at the top, as you can see, we started with SRAMs, and they serve as our cache memory. So SRAMs, as you know, in caches, they are optimized for speed and they offer very nice latency, but they really suffer in terms of area and capacity. We analyzed that in its standard cell, which uses your cross-coupled inverter, at the heart of the SRAM cell is what gives you these fantastic memory effect through positive regenerative feedback, as you can see in the butterfly hysteretic loops. And a major part of our discussion was focused on noise margins and stability, and we also saw how the 8T SRAM cell is able to provide adequate noise margins even at scaled technology nodes. Moving down the hierarchy, we looked at DRAM, which is our main memory, and we discussed that DRAM is more like an all-rounder in this game of memory and storage technology because DRAM balances both the latency and capacity. This trade-off is managed through this highly dense network of 1T, 1C or one transistor, one capacitor architecture. However, we saw that beyond just the device, the DRAM subsystem architecture, which takes form of this inverse pyramid, as you can see in your slides, something that we are familiar with, is what gave you these massive improvements in throughput, which helps us to somewhat circumvent the memory wall. Also, through very interesting concepts of dual data rate, refresh, and interleaving, you were able to somehow manage these throughput differences between the DRAM subsystem and your processor subsystem. Finally, we also saw that scaling the capacitor in the DRAM has been a major technological challenge which people have been able to overcome through advances in nanofabrication technology. Finally, at the base of the pyramid, we had your NAND flash for primary storage. Here, the critical thing was to have very high bit density. And this bit density was facilitated by having first a 1T structure, a 1T flash cell, which you can see on the slide. Second, by introducing very interesting NAND flash architecture. How you organize this 1T in a serial architecture is what we discussed in detail. The third important aspect was bit scaling, and as you can see, 3D scaling. All of these combine to give you the very high bit density. But of course, what we saw was all these factors give you non-volatile storage with very high bit density, but it comes really at the cost of very poor latency. Next, we move forward to look at the electronic or emerging non-volatile memories, which will also serve as storage class memories. First, we looked at the phase change RAM. Here in the phase change RAM, as you can see from the slides, the memory switches using heat, transitioning from a crystalline low resistance state to an amorphous high resistance state back and forth. So you had several interesting phase change materials such as GST, which can do this transition very easily. And by integrating this GST using intelligent thermal management techniques and intelligent device design, you can see the mushroom cell, you were able to make phase change RAMs very interesting candidates for emerging storage class memories. Next, we looked at resistive random access memories. Here we saw that the switching from the high to low resistance state was happening due to a conductive filament which was getting created and annihilated. We went into details of the two key subclasses which results in this conductive filament formation. We looked at valence change RAMs and also conductive bridge RAMs. However, we saw that individual crossbar arrays were not very useful because of sneak paths, especially when we are looking for large scale integration. And that we were able to solve by including a selector device which is called 1T1R configuration, and this is how you could scale the usability for large scale systems for the resistive random access memory. Finally, we came to the most exotic form of memory which comes from the magnetic degree of freedom, and this was your magnetic RAM or MRAM. And here, as you can remember, data was stored using the concept of tunneling magnetoresistance. This is a quantum mechanical concept where, depending on the relative magnetic polarization orientation between the free layer and the fixed layer, you can switch the device from parallel to anti-parallel configuration, where the parallel configuration had low resistance state. Remember the density of state argument that we gave, versus anti-parallel, which has high resistance state. And we saw several mechanisms of how do you switch the polarization in the free layer. So we looked at field MRAMs, we looked at spin orbit torque MRAMs, but the most promising thing was spin transfer torque, or STT, which uses a spin polarized current. Remember, by the direction of applying the charge current, you used to generate a spin polarized current, and that accumulation of the spin polarized current was giving a torque to the magnetic moment in the free layer and therefore flipping the orientation of the free layer. One important thing that we saw is that all these different kind of storage class memories, none of them had the perfect solution. So there were all kinds of trade-offs, both in phase change RAM, which had very high bit density but were suffering mostly in power, in resistive RAMs, where the power and CMOS scalability was very good, but reliability was a big concern, and magnetic RAMs or MRAMs, which had very speed and power capability, but the cost and scalability was a really big issue. So the idea is we are yet to find what is the ultimate universal memory in this storage class space, because each of these memories have some active trade-offs, and this is what remains to be seen in this field and an opportunity for future exploration. After finishing our deep dive into memory device technology, we turn our gaze to AI and machine learning, and we try to understand AI and machine learning from a very hardware-centric perspective. So at its core, we saw that how any workload in the AI ML algorithm is nothing but just hyperdimensional curve fitting. And as we show artificial neuron model, you can implement in principle the linear and the non-linear elements which are essential for doing any kind of curve fitting by taking inspiration from biology. And once you have this basic artificial neuron model ready, you can integrate a lot of them in form of an deep neural network. You remember why we call it deep neural network, because by adding more number of layers, you can in principle solve any kind of pattern recognition or classification algorithm. And this we saw in detail by looking at training and at inference. Remember, training was happening through this mechanism of back propagation of errors. So all of this looked very, very interesting in theory. However, The actual practical in hardware reality is really, really daunting. And as we gave in this example, that something that is so trivial like CAPTCHA for human beings like us takes large number of computational resources, both in terms of GFLOPS and hyperparameters, for these neural networks to solve. So when you combine this massive thirst for computational resources with severe penalties that von Neumann bottleneck presents, we saw that even doing simple classification tasks takes large amounts of energy and power. So we gave an example through this IBM work that your ResNet consumes roughly 385 kilowatts hours of power, which is equivalent to powering an Indian household for probably for 2-3 months. Therefore, the next motivation was to look at how do we solve this power crisis. So what we did was we started evaluating what is the efficiency of computation, not just accuracy. And this we did using a metric called watts per tera operations, as you can see on the x-axis. Definitely, while GPUs and TPUs, by doing multi-parallelism, we saw gives some advantage over generic processing units like a CPU, still there is an orders of magnitude gap remaining between our best hardware and the human brain, which is sitting right at bottom right corner. And this made us realize that it is essential to bridge this gap by studying and implementing brain-inspired principles, not just in software, but also in hardware. And this is the area of neuromorphic computing that we introduced. And here we saw the essential differences in neuromorphic architectures vis-a-vis the common von Neumann architecture. So unlike traditional computing, which separates logic and memory for sequential synchronous processing, we saw that brain-inspired architectures co-locate logic and memory, and they operate in a very highly parallelized fashion and an asynchronous event-driven nature, which is always communicated via spikes. So physically, this architecture relies on two key building blocks, and that is what we looked at next. We looked at artificial neurons and we looked at artificial synapses, and the overarching conclusion is that if you want to proceed towards neuromorphic computing, you better have electronic analogs for neurons and synapses, which are the fundamental building blocks for biologically inspired computing as well. And therefore, what we did was first we looked at the simplest leaky integrate and fire neuron model, and we tried to implement them in electronic fashion, mostly by using your ENVMs. So what was your LIF model? Your LIF model used to keep integrating your injected current into the neuron, but this integration was happening in a leaky fashion, as you can see through these red wavy lines, and post a particular threshold of your membrane potential, this model used to fire. Next, we looked at the most important thing, which is the basis of all biological learning and cognition, and that is your synaptic plasticity. Remember, synaptic plasticity was the ability to tune the weights of the synapse depending on a previous history of pulses. And there we saw that there are two key implementations which are required for synaptic plasticity depending on where you are going to implement them. If you use them in artificial neural networks, you want them to behave like a linearly tunable resistor. Whereas in spiking neural networks, the idea is to implement a resistor which can mimic spike time dependent plasticity. So finally, with this foundational understanding, we started looking at new architectures at the system level, which can help us bridge the gap, the large gap between your current day computing and brain inspired computing. So as you can see, first we looked at spiking neural networks, which rely on spike-based asynchronous computing rather than continuous numerical values, which is in ANN. And this event-based nature gave you large benefits in both power consumption and parallelism. So as we saw, the key promise of spiking neural networks was indeed in unsupervised learning, where these networks can learn on their own through unsupervised mechanisms like spike timing dependent plasticity, where the physical timing between these spikes naturally are able to train what happens to the weights. However, because these discrete spikes were non-differentiable, scaling unsupervised learning was always a very large challenge, and therefore people have come up with very clever techniques of supervised training, such as surrogate gradient descent and converting trained ANNs to SNNs. By using these two techniques, you are now able to implement spiking neural networks even for large scale models. Next, we saw that SNNs kind of represent a very high degree of biofidelity, but we also need urgent practical solutions that are implementable with our current hardware architectures. And this is where the paradigm of digital and analog in-memory computing was introduced at the last part of our course. So as you can see, in digital in-memory computing, we compute by performing Boolean logic within the memory array itself. And this we are able to achieve by cleverly modifying the peripheral circuitry and also the pulsing protocols. Conversely, as you saw, in analog in-memory computing, the approach was simply how can you drastically accelerate and make vector matrix multiplications very low power. And this was achieved single time step by exploiting fundamental physics by using both Ohm's law and the Kirchhoff's law. With this, we conclude a quick overview of what we covered in the past 12 weeks. And next, I want to start by introducing to you what the future trends in this very exciting area look like. So, as we explore these future trends, we must first recognize that advancing any computing systems requires a very holistic, cross-hierarchical approach and continuous co-optimization across both materials and devices, circuits and systems, and finally at architectures. But first, let us begin with what are the advances that are happening, especially in materials and devices. And as you can see, the primary advance that people are looking at is in the strategy of doing monolithic 3D integration. And this particular image explains what is the value of doing monolithic 3D integration. It is primarily the fact that you may have front end of the line compatible silicon CMOS logic, which performs very well for digital applications. But can you leverage other material systems which can give you excellent memory, neuromorphic, and other functionality? So by integrating this new kind of materials at back end of the line, remember what back end of the line was? It was the ability to integrate something with low thermal budgets around 500 degrees on top of traditional silicon CMOS technology, so that in the same footprint you can enhance functionality. And this in principle is the concept of more than more. So what are these interesting material systems that people are generally looking at? The first is the two-dimensional materials or 2D materials. Their key advantages is that they are ultra thin and they have atomic scale profile, and this offers very nice potential for very high density and very good electrostatics. This, along with wafer scale integration, allows you to really circumvent some of the challenges with your bulk semiconductor technology. The next thing people are actively looking at is this broad family of functional oxides. Now, There are several different kinds of functional of oxides which offer unique and tunable physical properties which enable novel computing. Amongst all these categories that I have listed, whether it's ferroelectric, smart insulators, topological insulators, and spintronics, all are being looked at very seriously. But I believe ferroelectrics are the most promising thing, and therefore we should do a deep dive into ferroelectrics. But before we do that, I must say that this concept of monolithic integration sounds very good in theory, but in practice there are severe constraints, and the constraints come from the quality of material that can be developed using back-end of the line processes which have stringent conditions for both processes and for thermal budget. And this results in not very good reliability of these materials which are grown at the back end of the line for monolithic integration. So let's do a bit of a closer deep dive into ferroelectrics, which represent one of the most exciting paths forward for memory integration, and I would really like to call them as the fourth electronic non-volatile memories. And first we will begin by looking at what is the difference between a regular dielectric and a ferroelectric. As you know, a linear regular dielectric has a linear dependence when you look at polarization versus electric field. However, a ferroelectric material follows a solid hysteretic curve, and this hysteresis is characterized by your coercive field and your remnant polarization. And as you know, any hysteresis which is occurring can give rise to very interesting memory effect. And just as we studied in our SRAM section, any hysteresis can also be characterized by your W-shaped potential barrier. But the real question here is, why is this W-shaped potential barrier there? And the answer to this is looking at the switchable ions inside a particular perovskite material. So the material in question I have taken is barium titanate. Explaining ferroelectricity for these perovskites is very easy. As you can see in the box of cubic structure, you have titanium right at the middle, and this titanium position has two stable states. Once in the first state, the titanium is slightly above, and this represents the up polarization state, and then where titanium is slightly below, and this is your down polarization state. And both these states are actually a bit more stabler, as you can see from the energy landscape diagram, than your original state. And that is why you get this memory effect, because the system can stay either in this potential well or in this potential well. All this is very nice, but how do we leverage this in devices? And this is where things become very interesting. As you can see, you can leverage these devices by using the same 1T, 1C structure, but instead of using a regular capacitor, you have replaced it with a ferroelectric capacitor. And this is very similar to DRAM, but the interesting thing when you replace this standard dielectric capacitor with a ferroelectric capacitor is it starts giving you non-volatile DRAM effect. However, it comes with a major catch, that the reading, when you do the reading, what you essentially do is you try to find out whether the ferroelectric is in up polarization state or the down polarization state. But when you try to do that, it destroys the polarization. And therefore, although this is non-volatile in principle, the read is a destructive read, and this must always be followed by a specific write back. And to fix this, people have come up with another technique, and this is of a ferroelectric FET, which is just a 1T version, and therefore it is expected to replace NAND flash. So what is the principle of working for ferroelectric FET? It's very simple. By switching the polarization, you can either induce electrons at this particular layer, which is at the interface of the ferroelectric and the p-type substrate. If you have up polarization. If you have down polarization, you will be able to remove these electrons. And therefore, just like your NAND flash worked by having two different threshold voltage values depending on trap charges, this is also the same principle. However, we should understand that while there are several advantages to ferroelectric FETs, they come with their own set of challenges. First, let's discuss the advantages. As we discussed, they are essentially non-volatile, and even the switching is ultimately much lower power compared to other ENVMs. And what has really changed the game is the CMOS compatibility. The earlier set of ferroelectrics, the classical perovskite ferroelectrics, which was barium titanate, were not really compatible with CMOS processes. It was very difficult to grow them using CMOS processes. But now, by doing doping of your regular hafnia, and this is called HZO or hafnium doped zirconia, people have been able to induce ferroelectricity even in your regular dielectrics, and this could prove to be a game changer. However, there are still very big challenges in terms of both scalability and also in terms of reliability. FE technology or ferroelectric technology is something to really watch out for. Now, moving up from the materials and devices to the system level integration, let us discuss how we bring all these together through advanced packaging. As you know, and we have discussed it, traditionally, computing and memory chips were placed on a conventional printed circuit boards with these long interconnect wires. And this is what was one of the key physical reasons for the von Neumann bottleneck. And we discussed briefly in our course that by using heterogeneous integration, this is a very interesting packaging technology where completely separately manufactured dies. We gave the example of a DRAM chip made in South Korea in SK Hynix and a logic chip made in Intel in the US. They are brought together in Singapore and they are packaged into a compact system in package or SIP. So we already looked at 2.5D integration where this was done using a passive silicon interposer. The latest generation and is 2.7D where you have active silicon interposers. By adding power switches and other active elements within the silicon interposer, you can enhance the functionality of these SIPs and thereby improving the system level performance. However, we should recognize that the ultimate goal is to have 3D direct heterogeneous integration. So as you can see from this particular slide, here the memory stack is not placed side by side, but it is vertically stacked right on top of the computing die using this very thin through silicon vias. And this results in the maximum possible footprint advantage and extremely short interconnect. But we have to recognize that these two have very severe challenges. The first challenge is that of poor thermal management. These chips get very hot when they work on top of each other and there is no place for heat to escape, and therefore thermal management and these high implementation costs could be a showstopper from making commercially viable 3D integration. Finally, we step into the architectural level and look at how computing is evolving from parallel computing to distributed computing. Now, we saw some features of having parallelism. Earlier in generation 1, we just had one single large core which was doing all kinds of activities. This was split into multi-core architecture for some parallelism and also managing the heat and the frequency limitations that were coming due to CMOS scaling. And then the third generation of GPUs, which had many small cores which were crunching out the workloads in a parallel fashion. However, the fourth generation represents a really different outcome and a very different approach. And this is true distributed computing. So what is happening in the next or the fourth generation of computing? In this paradigm, the CPU is no longer performing your heavy computational tasks. Instead, it acts simply as a scheduler and as an orchestrator. What it does is it analyzes the diverse incoming workloads like AI, video, or other data tasks and strategically schedules and routes them to highly specialized task-specific accelerators. And this has been already nowadays implemented in Apple's M2 or M3 chips, where you have your neural processing units along with your GPUs and your regular CPUs. And looking forward, we have to understand that while current implementations are of these accelerators are essentially digital in nature, future implementations of these accelerators will have all the elements of novel materials, devices, and systems. In systems, we will look at, for example, spiking neural networks to do all event-based computing, and in-memory computing, which can behave like accelerators for doing heavy-duty vector matrix multiplications, which is currently done using digital GPUs. So, in a sense, the message that I want to give to all the people who are very interested in this field, that a modular approach will not work. A person cannot be just a device engineer or just a systems person or just a circuits person or just a architect or a system architect. A complete cross-hierarchical co-optimization is absolutely essential to make a dent in this particular field and solve the problems of tomorrow. And this is precisely the approach we try to take in our research group. In our research group, we try to look at these many complex problems by equal emphasis on experiments and also in theory and simulations. In the field of experiments, we look at novel materials and their device implementations. For example, in our group, we look at 2D materials and also at self-healing organic crystals. We do growth and synthesis of these materials and also fabricate 2 and 3 terminal transistors and memristors. Next, taking these devices forward, we perform extensive electrical characterization in direct current and pulsed regimes. And this helps us to give you very interesting properties, as you can see, of ferroelectric hysteresis, potentiation and depression, and also spike timing dependent plasticity. So what do we do over here? Do we stop? No. We take these electrical characterizations, and this serves as the engine for our device modeling effort. Why do we do device modeling? In device modeling, we get two main advantages. We really try to understand what are the fundamental mechanisms which are at play when these devices are working. And this gives us the flexibility to engineer better devices. Not only that, because experimental exploration is very expensive, our calibrated device models are able to predict what would be the behavior of these devices when they are pushed to really corner cases. And this serves as an impetus to our final objective, which is trying to do a system level modeling. Through system level modeling, we understand the fabricated devices and their analogous models. How do they behave when they are subjected to system level tasks such as in-memory computing and stochastic computing? These are computing regimes which are beyond von Neumann computing. And by completing this, it gives us an idea of what are the challenges to be solved at materials and devices level. And this is how we complete the entire arc. Finally, last but not the least, I want to close out our final lecture by acknowledging all the wonderful people who made this course possible. As you know, this is a very interdisciplinary course, and one particular person or a faculty like me cannot know all different aspects. But it was a great learning experience for me to learn from different colleagues of mine. I have tried to acknowledge few of them. First, I would like to thank Dr. Yashasvi and Dr. Girish from Micron, who really helped me understand NAND flash from a very technological perspective. Next are my friends from IIT Hyderabad itself. From computer science engineering, we have Dr. Rajesh Kedia, and from our own department, we have Dr. Sumona, who gave me a lot of ideas of these system level architectural bottlenecks, especially in convolution neural networks. Next, I would like to thank Dr. Gajendra for a lot of insights on analog peripheral circuitry, and our spintronics expert, our colleague Dr. Chandrasekhar Murapaka, who helped me the aspects of MRAM. And finally, my two very good friends, Dr. Oves and Shritosh. One is from IIT Hyderabad and Shritosh is in ISC Bangalore, for a lot of discussions about memristive behavior in lot of these novel materials. Next, I want to thank my research group and the specific teaching assistants who were involved in a lot of intense discussions, video proofreading, and making the assignments for our course. Special mentions to Krupakar, who is the main TA, Karthik, Piyush, Anil, Balaji, Tejas, Ram Mohan. Thank you very much. Last but not the least, I want to thank my IITH classroom students from 2003, 4, 5 and now 6 batch, and my NPTEL course students. Thank you very much for your attention, for your questions, and most importantly, it is the encouragement of all these previous batches which really motivated me to put this course in NPTEL platform. Last, I want to thank the NPTEL team, both at IIT Hyderabad and at IIT Madras, for making this a very smooth journey and taking care of all the logistical details. Thank you very much. It was a wonderful journey that we undertook. Hope you enjoyed it as much as I did.